Hello, my name is Derek Nollsch, and I'm working with Eric Calbonero and Casey Reilly on our IME 482 project, the Avenue Redesign. This is our senior project, and our technical advisor slash administrative advisor is Karen Bangs. Let's move into some background for our project. The idea for this project came about from the Director of Operations for Campus Dining, Greg Yeo. He explained that VG's Cafe near the freshman dorms is going to be closed for remodel during the upcoming school year. The current VG's demand will have to be distributed between the existing on-campus restaurants, including the Avenue Food Court. This would increase customer demand for the Avenue. Additionally, the ever-growing student population at a historical rate of 3% per year would further increase demand. Finally, campus dining plans to eliminate meal credits, which also may increase customer demand for the Avenue. Our problem statement is as follows. Due to the expected increase in customer traffic, the Avenue is looking to accommodate additional demand.
This is the current state of the Avenue. This area shows where the food is being served and does not include the seating areas. There are currently 7 restaurants, which include Chick-fil-A, Fusion Bowl, Topango's, City Deli, Grab and Go, Beverages, and a salad bar. These restaurants are situated around the perimeter of the space, with the salad bar located in the center. There are 6 available registers, and they are stacked on top of each other with checking lanes on either side to make best use of the limited space available. Here's a 3D representation of the Avenue. Typically, a customer will enter the system, go to one of the 5 main restaurants before going to the beverage station located on the left or the salad bar located in the middle before checking out. As you can see, the space is very limited, and this creates a lot of clutter during peak hours when there's many people in there. Here we've created a Pareto chart to help our team identify which areas of the Avenue we should focus our improvement efforts on. This chart shows the average amount of customers that go into each section and restaurant of the Avenue every day. As you can see, Chick-fil-A and beverage station make up a huge portion of this, accounting to about 70% of the cumulative total. The difference between Chick-fil-A and the beverage station, however, is that Chick-fil-A has a much larger processing time and a larger demand. These two factors combined make Chick-fil-A the bottleneck in our system. Now that we have identified the bottleneck, we can move forward in improving our system.
The Avenue is open from 7 a.m. to 7 p.m. Monday through Friday. Our group decided to focus on peak hours, assuming that the model would hold during non-peak hours. Peak hours were determined to be from 11 a.m. to 2:30 p.m. Demand at these times were over double the normal demand. Inter-arrival times for the Avenue and processing times for each restaurant were collected from time studies done at these peak hours. With the aforementioned times gathered from our observations, we were able to develop the simulation model we used to model the system. As you can see, a customer enters to the left and then enters a decision node where he or she decides which restaurant to go to. Once the customer has been served, they can travel to the beverage area or move on to the collection point where they can choose the least loaded register to then exit the system. In the model, we were able to obtain baseline data for the current system. We gathered information for the entire system as well as for the bottleneck restaurant, Chick-fil-A. The metrics for the Avenue are listed to the left, and the metrics for Chick-fil-A by itself are listed to the right. We will look at these metrics to quantify improvement for the project. Please keep in mind that this is an iterative model, so these metrics may change in the future as our model continues to develop. In order to study the model further, our group conducted 3 experiments to the simulation model. For our first experiment, we tested the current system with an increased arrival rate. The group chose to increase the arrival rate by 10% due to the 3 contributing factors mentioned beforehand. Our breakdown is listed below. It is important to note that these are conservative estimates for our model. Here are the results from experiment number 1. As you can see, our total customers served increased by over 100. This can be mostly contributed to the increased arrival rate and says nothing about the performance of the model. The metrics that do determine the performance of the model are average customers in system and, more importantly, average time in system. We can see that both of these almost double during the experiment. This result was expected and somewhat justifies implementing improvements to decrease these metrics back down to normal. In experiment number 2, we tested the system when each restaurant has equal demand. This excludes beverages, since other restaurants linked to the beverage station as well, already impacting its demand. Our hypothesis was that this would decrease time in system and improve system performance. Here are the results for experiment 2. To our surprise, the system performed very poorly. The total customers served decreased, and the average number of customers in system and time in system more than doubled. We determined that this occurred because of the varying process times that are not usually as constrained with a smaller demand.
For our next simulation experiment, we chose to take the processing times of all the different restaurants and set them equal to the processing time of the bottleneck restaurant, Chick-fil-A. This was about 16 seconds, and we expected these changes to reduce the variability in all areas of the system. The results of this experiment show that the total customers served increased slightly, while the average customers in system and the average time in system decreased quite a bit. These experiments gave our group some very useful results. Our first experiment showed us that with the expected increase in the amount of customers coming through the avenue, it would result in unwanted increase in time in system. Our second and third experiment gave us some very interesting results. It showed us that although we can spread out the demand throughout all the restaurants in the avenue, more importantly, we need to decrease the processing time in each restaurant. Ideally, we would not only decrease the processing times, but also standardize them so that each restaurant takes about the same time.
As a result of our careful study of the avenue, we recommend several proposed improvements. First off, we recommend that they reduce the size of the salad bar. This would free up space in the avenue and lead to less clutter in the restaurant. Next, they should add an additional restaurant with the necessary equipment, such as a hood and refrigerator. This would include remodeling existing sections of the avenue, like demolishing and adding additional walls. Next, they should simplify menus to standardize processing time. As shown by experiment, a consistent processing time reduces the total time in the system. Finally, they should add 2 additional point-of-service stations with 1 associated queue. This would reduce loads on the existing point-of-service stations. Here's a schematic of our proposed layout. Along the bottom, you can see the addition of 2 registers with an additional queue. Above, you can see the addition of a smaller salad bar to reduce clutter in the avenue. In the dotted lines to the right, you can see the repositioning of the grab-and-go items to account for the addition of a new restaurant. Finally, along the right side, the new restaurant called for demolition of several walls and addition of several more. This is a 3D model of our proposed state of the restaurant. The 3D model helps to visualize the freed up space from our proposed improvements. Along the right side, you can see the addition of a new restaurant with a bar area surrounding it, as well as the addition of a new wall. Here's the financial justification for our project. It is divided between yearly and daily revenue. For the current state of the avenue, this yields over a $2.2 million yearly revenue. After redesign with a 10% increase in sales, this would yield over a $2.4 million revenue, with a net revenue increase of over $220,000 per year. This translates to a daily revenue of over $1,600 per day.
Here's an estimation on how much it would cost to implement all our improvements to the avenue. These improvements include demolition of the wall, building a new wall, all the restaurant equipment, adding a new checking lane, and the addition of a new salad bar. All these changes add up to about $33,500.
That concludes our presentation. Thank you for your time. If you have any questions, please contact Eric, Derek, or Casey at the shown email addresses. Thank you.